Let's start today's seminar. Today's speaker is Seán Mee from University of Graz. We'll talk about on the construction of series of composite dark matter. Please start.
Great. So thank you, first of all, Sarah, for the invitation. Thank you, everyone else, for having me here today to talk about some of what we've been working on. Hopefully you find it interesting and we have some good conversations. My name is Seán Mee. I'm originally from Ireland, but I'm working now as a PhD student at the University of Graz. We work primarily on strongly interacting theories of dark matter. And what I'll be presenting today is predominantly based off our recent work. This is the archive number. And these are our collaborators. So Suchita Kulkarni, who's in the audience, Axel Maas, Marko Nikolic, Josef Pradler, and Fabian Zierler. So I guess I'll get started. So what I'll be presenting today, just a brief outline, is I'll provide the briefest of introductions to dark matter, which I'm sure most of us are at least on the surface level familiar with. I'll describe some candidate models for particle dark matter. I'll talk about strong interactions and composite DM and some of the nice properties that these sorts of theories have. I'll then be focusing in particular on symplectic gauge theories and particularly on Sp4 gauge theories, describing the symmetries and the low energy spectrum of these theories. I'm going to describe how, in the most minimal way, we can couple these dark sectors to the standard model, talk about all the explicit symmetry breaking patterns and the decay modes of the composite states. And finally, I'll provide some outlook and conclusions. So the group that produced this work is the strong DM group. The idea behind this group is for people with varying disciplines to work on the same project with a focus on strongly interacting theories of dark matters. We take several approaches in characterizing the SIMP paradigm. So that's the strongly interacting massive particle paradigm of dark matter. And I'll be explaining a little bit more what that means as we continue. Oh, excuse me. Excuse me, I'm in the middle of a talk. That's okay, sorry. Sorry about that, guys. And of course, we want to have a close collaboration between people from a wide variety of disciplines. So in particular, between lattice theorists, cosmologists, experimentalists, and phenomenologists. Okay, so dark matter should require, I guess, very little introduction. It's one of the biggest unanswered questions in physics today, with evidence on a huge variety of scales. We know it makes up approximately 84% of the non-relativistic matter and about a quarter of the total energy budget of the universe. I've included just two classic pieces of evidence for dark matter here. First is evidence which comes from bullet clusters, where what we can see is that the spatial offset of mass peaks is pretty far from where the bulk of the visible matter is, right, indicating that there's something missing. And the second is, I guess the most, famous piece, which is from galactic rotation curves, where in contradiction with the predictions of Newtonian gravity, rather than trailing off as 1 over the square root of r, the velocity of matter beyond the bulge remains approximately constant. Right? So faced with these pieces of evidence, we can come to 2 different conclusions. Either there's matter present, which we can't see, or our understanding of gravity doesn't really scale to galactic scales. But we'll be taking for granted, I guess, that dark matter is actually the correct explanation for these observations going forward. Okay, so if dark matter is a particle, what are the properties that we expect it to have? Well, we expect it to be stable or at least very long-lived, with lifetimes at the scale of the age of the universe. It should be very weakly charged under the standard model group, right? So we make now a distinction between weakly charged under the standard model group and weakly charged in general. When we talk about strongly interacting dark matter, we really refer to strong interactions within the dark sector itself. It should be mostly non-relativistic at the time of matter radiation equality. Right? So we use the terminology cold going forward to describe this. And finally, it's probably not a standard model particle. Of course, there were neutrinos were initially seen as a natural candidate, but have since been ruled out for a number of reasons. I know that this is not a completely decided on statement, because there is, I still think, the stable sexa quark hypothesis which survives, which potentially could have a dark matter candidate within the standard model. Okay, so just to quickly outline some classic particle candidates for dark matter, I'll first talk about the standard WIMP, or weakly interacting massive particle. So under this paradigm, the dark matter is actually a thermal relic, which freezes out through an incomplete annihilation process. So this is a formula which gives us the contribution of the dark matter to the total critical density of the universe. And what we see is that for weakly interacting particles, that is for an alpha approximately 0.01, and particles at the weak scale, so dark matter mass of around 100 MeV, 100 GeV, we reproduce the observed relic abundance of around 0.1. But it's been known now for a while that this isn't the only route to the relic density. There's a number of other routes we could take. So in particular, the one of interest for us is this 3-to-2 effective vertex, where we have sort of a cannibalization process where 3 dark matter particles annihilate into 2. So what we know is that if this is the primary number changing process, then we can make an estimate of the dark matter mass. And for this combination of variables, we have a dark matter mass of around 100 MeV. So in layman's terms, what this means is that we have a strongly interacting particle which freezes out at late times. That's essentially what this choice corresponds to. And this gives us dark matter mass of the order of hundreds of MeV. So it was noticed that in the standard model, exactly these sorts of interactions are sourced by the Bess-Sumino-Witten action in QCD. And so this has spurred a new interest in dark matter as a composite particle in a QCD-like hidden sector. So when we talk about QCD-like, what we mean is we have a sector with some confining symmetry where our quarks, or well, whatever we want to call them, our fermions, confine at some scale and give us bound states. And really these bound states are what are going to make up our dark matter. So thankfully in isolation, the lightest states in this hidden sector are going to be completely stable. So these are some of the nice properties then that strongly interacting theories of dark matter have almost naturally, right? So first of all, in isolation, we have a fully stable dark matter. The stability is guaranteed just by the fact that the sector is decoupled from the standard model. We get self-interactions which come mostly for free. So in particular, we get these 2-to-2 processes from the kinetic terms in our Lagrangian, and this 3-to-2 process which allows our dark matter to freeze out. And finally, I think maybe another big advantage that these sorts of theories have is that the freeze out happens completely in an isolation from the standard model, which means constraints from things like the relic abundance, for example, actually don't constrain some sort of coupling necessarily between our dark sector and the standard model, but instead the spectrum of the dark sector itself, right? So in particular, masses and decay constants. So this is a plot which it's for SUN dark matter, which shows us which parts of this parameter space reproduce the observed relic abundance. Okay, so now just a quick refresher on how strong dynamics work in the standard model. So how it works is that at the UV level, we have some scale where the strong coupling diverges, and now quarks confine only into color neutral composite states, right? So pions are sourced by the bilinears of the form QQ bar. And they can also be characterized as what we would call the pseudo-Nambu-Goldstone bosons of chiral symmetry breaking. So when we talk about chiral symmetry breaking, what we refer to is the breaking of this global flavor symmetry, which allows us to separately rotate the left and right-handed components of our quark fields. Excuse me. So this chiral symmetry is broken by the psi bar psi condensate, which acquires some non-zero vacuum expectation value and breaks this symmetry down to just the diagonal subgroup. We retain just the SUNF diagonal global subgroup. So by counting the number of broken generators, we can count the number of Nambu-Goldstone modes that we should get in our spectrum. We just should highlight here that when we talk about pseudo-Nambu-Goldstone bosons, all this means is that these aren't perfectly massless modes, right? Our quarks can in principle carry some finite non-zero mass, which means after chiral symmetry breaking, our new Goldstone modes are not going to be perfectly massless. They're going to carry some mass, which is governed by exactly how this explicit symmetry breaking occurs in the UV. Okay, so once we have our pseudo-Nambu-Goldstone bosons, what are the methods that we use to study them? So one method we might use is lattice field theory. So this is a method by which we can simulate the full theory. It's a totally non-perturbative description and allows us in principle to access low energy constants. So the most famous examples here would be masses and decay constants of our bound states. There are some limitations here, which is, first of all, it's costly, especially if we want to work close to the chiral limit, or we want to work in the limit where the quarks are extremely light, where their masses are close to zero. And finally, of course, we need to have a good understanding of lattice systematics. Right? Otherwise, we're going to get results which are very, very noisy. The second method which we might use, which is what I'll be talking about a little bit more today, is chiral perturbation theory, which is a systematic expansion in the small momenta and masses of our pseudo-Nambu-Goldstone bosons. So here we need to now highlight the difference between, well, we call this a perturbation theory, right? But it is not perturbative in some coupling, the way we would understand from more familiar gauge theories, I suppose. Here, our expansion is in terms of small energy scales in our dark sector. Did I hear someone on mute there, or maybe not? Well, if anyone has a question, feel free to interrupt. So in principle, this expansion should respect all of the symmetries of the UV action. If there are flavors which are too heavy to be treated in this way, they can just be integrated out, and then their influence will be seen in low energy constants associated with each term in our expansion. And of course, there are limitations here as well. So if we want to work beyond leading order, we in principle have to construct every term at a given order, which is consistent with the symmetries. Each of these guys is going to have some new low energy constant. And these are in principle going to require some extra input. It's not going to be something that we can always fix analytically just from the action itself. Often we'll need some extra experimental data or input from Lattice. Okay, so as I said at the beginning of the talk, what I want to cover today is more symplectic gauge theories and less of the familiar Sc3 type gauge theories, which we would, I guess, understand a little bit better from QCD studies. So just to highlight some of the key differences between Sc3 and Sp4. Well, first of all, we actually have an expanded flavor symmetry compared with the SUN case. After chiral symmetry breaking, we retain a larger flavor subgroup. And by counting the number of broken generators, we can see we actually have a greater number of Goldstones, right, just from chiral symmetry breaking. So for a non-vanishing 5 Goldstone vertex, this 3-to-2 interaction that I showed you earlier, we need at least 5 distinct pseudo-Nambu-Goldstone boson states. So this means that for an SU3 gauge theory, the minimal realization is for 3 quark flavors. And we can see that by just checking, by just looking at the number of goldstones we get for each number of flavors. If we choose 2 flavors, then we get 2 squared is 4 minus 1, only 3 goldstones, right? So we wouldn't actually have enough to generate this 5 goldstone vertex, which we need for this SIMP-like freeze out. But a more minimal realization is possible if we now consider fermions in pseudo-real representations. So for example, the fundamental representation of Sp4. Here we can see that for NF equals 2, we get 4 plus 1 is 5, 2 minus 1 is 1, 5 total goldstones, which means we get a non-vanishing goldstone vertex for only 2 flavors. So this is, I guess, part of the motivation for why we consider Sp4 theories, right? Is to first of all understand these new different types of gauge theories with pseudo-real fermions, and also because it's actually a more minimal realization of the SIMP paradigm, which we've hopefully given you a little intro to. So this idea of pseudo-reality, what does this really mean? Well, for a pseudo-real representation, what this means is that it has the property that it's isomorphic to its conjugate representation, right? So we can show that the fundamental representation of Sp4 is pseudo-real by using the defining property of the symplectic group, right? Which is that there exists some matrix S, right? Which when acting on an element U of Sp4 gives you the conjugate element, okay? So really, this is the defining property of Sp4, which is that it's the subgroup of Su4, which has this property, right? Where you have this matrix, which allows you to transform an element to its conjugate. So at the generator level, this shows us that we can transform a generator into its conjugate, which is exactly this property of pseudo-reality we were talking about. And what this means is that we now have this symmetry between particle and antiparticle, and we have an expanded flavor symmetry. And this is really what's responsible for the enlarged spectrum compared to standard SUN type gauge theories. Okay, so just a little diagrammatic explanation now of the difference between complex and pseudo-real gauge theories, just providing the global symmetry which is present at each step, right? So what we should be noticing is that at each step, the flavor symmetry for the complex case is actually a subgroup of the flavor symmetry for the pseudo-real case. So this should illustrate that we have this enlarged flavor structure. Nevertheless, let's move on. So yes, the way we can see this is because of the larger flavor symmetry, we have this 4-dimensional flavor space. We can build our bilinears now out of elements of this matrix, psi. And this shows you what this enlarged symmetry really looks like. So if we go back, this SU4 global flavor symmetry is really a global symmetry which allows you to rotate unitarily these 4 guys into each other. Okay. So that's really the meaning of this, right? We can exchange something like the left and right-handed components of our quark fields with each other, right? They can be independently rotated into one another without changing the action. Okay, so just to provide a little description of exactly how chiral symmetry breaking works now for symplectic gauge theories. We have, of course, this expanded flavor symmetry, no longer SUNF left cross SUNF right, but instead an expanded SU4 global symmetry. This time, our symmetry is broken not by a psi bar psi condensate, but by a psi transpose psi condensate, right? So this acquires, this acquires a non-zero vacuum expectation value and breaks our SU4 down to the subgroup Sp4, which means we have 15 minus 5 equals 5 pseudo-number Goldstone bosons in our spectrum. But what does this spectrum now actually look like? Well, our theory contains all the standard meson states of QCD, right? So our pi 0, our pi plus, our pi minus, these should be present in our spectrum. But it contains also extra states because of this expanded flavor symmetry. So I've written here also that the theory contains no baryons. This might be, people might maybe semantically disagree with this. Really, all I mean is that we have no bound states which have free fermions present, for example, right? There's no color neutral combination that we can build out of an odd number of fermions. Really, our baryons are more like quark states, and these are actually going to be just present in our low-lying spectrum anyway, right? So really, it's maybe not correct to say there's no baryons, but the baryons in this theory are totally degenerate with the Lattice mesons as well. Okay, so in what follows, we consider now only the case of degenerate mesons, or degenerate fermions, excuse me. Okay, so yes, as I mentioned, Sp4 theories allow the construction of color neutral states of quark pairs and anti-quark pairs. So, and because of pseudo-reality, these actually form part of our Lattice Goldstone multiplet, right? So what this means is that along with the standard U bar D states, we also have these sort of U transpose D states, which are actually going to be totally degenerate with the rest of the Goldstone multiplet. So just a little look at exactly what the spectrum looks like. Rather than 3, we have 5 Goldstones, right? We label them A through E. Rather than only 3 Lattice spin 1 states, we actually have a total of 10. And I'll explain exactly what that is in a moment. Okay, so now that we know a little bit about what our spectrum looks like, we want to now understand exactly how the dynamics of the PNGBs can be described. Well, the answer is that they can be described through fluctuations in the orientation of the vacuum condensate. So what this means is that we look at our, maybe I should scroll back and just show you exactly what I mean. So our vacuum, by which I mean this guy here, we know now that our Goldstones are going to describe transformations which they transform between some manifold of degenerate vacua, right? So what we do is we perform a transformation of the coset, so the SU4 to SP4 coset, on this expression here, and that's what gives us the chiral field sigma. Okay. So what we do is we take this chiral field and we build our chiral EFT out of it. The idea is, to a given order, we construct all terms which are consistent with the symmetries of the UV Lagrangian, right? So at leading order, there's just 2 terms, and they take this form, where this first guy is our kinetic term. F pi is now our pion decay constant, and this second term is what describes the masses of the bound states. Okay, so we've written down our leading order chiral Lagrangian, which should describe our Goldstones well, at least close to the chiral limit. But there are other states in our hidden sector which may be interesting from phenomenology. So in particular, one thing which is interesting for us is the spin 1 multiplet. So the multiplet which is analogous to the multiplet of rows in QCD, since this can play an important role at colliders and elsewhere, right? So in order to couple these to the EFT, what we do is we make use of this idea of hidden local symmetry. Okay, so I'll describe now exactly what I mean by that. So what this allows us to do is to couple our Lattice spin 1 states as dynamical bosons to our PNGBs, right? So the way that we do this is to take a second copy of our global flavor symmetry, so in this case an Sp4, which is completely broken by the condensate. So what we get is a number of actual massless Nambu Goldstone modes, which appear in our theory, And just in total analogy with the Higgs mechanism, these provide mass to all our spin-1 states, right? We can always gauge these away, provide longitudinal degrees of freedom to our gauge bosons, and they acquire a mass, right? So here's just a diagrammatic explanation of what I mean. We have one symmetry which is global, the other which is gauged. Then the non-vanishing VEV of, first of all, sigma, which we've discussed, and this other scalar field, break the symmetry down to just this remaining global Sp4. So in this paper, they actually fix the masses of the vector states completely in terms of the low energy constants of this full SU4 cross SU4 theory. But for us, we just retain the rho mass as a sort of a free parameter. And in fact, this is really one of the inputs for us on the lattice, right? So our collaborators who simulate this theory on the lattice, they actually use this rho mass as an input parameter. But really the idea of hidden local symmetry is just to couple the vector bosons as if they were gauge bosons, right? And give them some mass, right? And that's really what we intended to do with this approach. So what is it that characterizes the low energy states then? So in our full UV theory, we have some energy scales. So mu, well, this is the chiral condensate, if you like, the quark masses, and this scale lambda at which our theory confines. And these must become encoded somehow in the low energy constants of the EFT. So just if we're thinking about the particles I've talked about so far, what we mean is the pion mass, the rho mass, and their corresponding decay constants, f pi and f rho. So lattice computations of these have already been available for a little while for degenerate fermions. So I'll just show some fits from some of our friends in Swansea. So what we have here really are just fits for the masses and decay constants of various states in the dark sector. Right? So one thing that we wanted to talk about, which is well, in particular new to our paper, is to talk about how these sectors will look if we give them some minimal coupling with the standard model. So since, of course, this hidden sector in total isolation would interact only gravitationally, it becomes interesting to think about what are the simple portals that we could add to this, and what's the sort of associated phenomenology. So I guess the most typical extension discussed is a U1 extension, probably because of simplicity and familiarity. So that's actually what we consider going forward. So one example, which, well, this is the one that we talked about the most, I guess, is the dark photon. So here we have some new U1 symmetry under which all of our dark quarks are charged. It's broken by some dark Higgs mechanism, which means that our U1 gauge field is going to acquire some mass. And it interacts with the standard model through the weak hypercharge portal. So we allow our new field, V, to kinetically mix with the weak hypercharge. And this is going to provide a portal between the hidden sector and the standard model. And really what this means is that we're going to have dark matter, which is so-called milli-charged under the standard model group, meaning that it has some very, very small charge, which is controlled by this small parameter epsilon. Okay, but now in the presence of these U1 couplings, in principle, our remaining flavor symmetry, so our global Sp4, could be broken. So what we know is that for sure the symmetry breaking in our effective theory needs to match that of the UV Lagrangian. And so it was important for us to understand these symmetry breaking patterns since they have important implications for the stability of our bound states, right? So in the UV action, the symmetry breaking term just schematically is of this form, okay? Where Q is now some charge matrix in flavor space. And so the idea then was to perform a flavor rotation and work out what exactly is the symmetry violating term, so that we can work out exactly what symmetry is conserved after a particular charge prescription.
Hello, hello.
Oh, hello.
Yeah, in this slide, what is V and what is Q?
Oh, excuse me. Yes. So V is the gauge field that we've introduced. So V is this U1 gauge field, right? This is our if you like, this is the dark photon field itself. Excuse me, I should have made that more clear. That's my fault. And Q is the matrix in flavor space, which gives the charges to individual quark flavors, right? So this is like a 4x4 matrix, which basically describes the couplings of the various quark fields to the dark photon. Does that answer your question, or would you like me to elaborate?
Yes, thank you.
No problem. Yes, thank you for asking. Perhaps that should have been more clear.
Sorry, could I also ask one question concerning the dark Higgs mechanism?
Yes.
So you have the mixing of the dark photon with the standard model gauge bosons.
Yes.
Do you also have interaction terms between the dark Higgs and the standard model Higgs, like a h squared, phi squared term?
I think in principle this can't be forbidden. So this would be present. Yes, so that's a good question, and that becomes very an important thing to consider when our dark Higgs is also responsible for the masses of the dark quarks. For us, that isn't the case. We add these by hand because, well, since there's no chiral couplings in our dark sector, there's no need for the Higgs to be responsible for those masses. If that were the case, then yes, this would be actually another portal, right? Because if we have a dark Higgs, we really can't forbid it mixing with the standard model Higgs. Now, if that Higgs also talks to the dark quarks, then that's another portal, of course.
So you have, in principle, a Higgs portal and a vector portal present, and you're focusing on the vector portal here.
I'd make an even stronger claim than that. We would have a Higgs portal if the dark Higgs communicated with our dark quarks. But since there's no distinction in our dark sector between left and right-handed quarks, there's no real need for a Higgs to be responsible for their masses, right? Those can be added separately by hand. So you're right. There would be a Higgs portal if the dark Higgs gave mass to everything in the dark sector, but since it's really just a tool for giving mass to the dark photon, ultimately it's not really a part of our theory. But you're right, it in principle could be, right? If we were willing to relax that and say the dark Higgs is now responsible for the masses of all the dark states, then yeah, of course we would have a second portal.
I see.
Exactly
and
right.
So the fermions in your dark sector, are they chiral or vector-like?
They're vector-like.
They're vector-like. Okay, so they can get a mass independent.
Exactly.
Just from that. Okay, thank you very much.
No problem at all. No, thank you. It's a good question. Yes. So the idea is then to take our interaction term, perform a flavor rotation, and work out the conserved symmetry. Right? And so we hoped by doing this, we might be able to get an idea of, well, the stability of the dark sector states. So if a goldstone can decay, it's going to do so through the AVV anomaly. So in particular, this vertex, which comes from the gauging of the Ves-Zumano action. So you can think of this in sort of an analogy to the way that the pi0 decays in the standard model, right, to pairs of photons. Of course, in principle, our V can be heavy, which means that we might have to let our pi0 decay to pairs of fermions, but nonetheless, this is going to be the leading order interaction, which lets the pion decay if it does so. But this can only occur, of course, if the particle is not protected by some symmetry. It doesn't carry some charge which protects it. Or in other words, that it falls into a trivial representation of whatever remaining flavor group is left. So we worked out exactly for all the various charge assignments that we could think of what the remaining symmetry is and what the sort of multiplet structure of our states looks like for each charge assignment. And so what we worked out is that there are actually a couple of flavor conserving assignments, that is non-trivial charge assignments, which actually conserve some non-trivial part of the flavor symmetry. So these two diagonal ones in particular, and this off diagonal, give us essentially, well, they break our Sp4 down to Su2 cross U1. And what we have in each case is actually a triplet of states, right? So what we have is a triplet under Su2, and then a remaining pair of states which are actually protected by U1 charges. So this is kind of interesting, and it sort of highlights the key difference between these sorts of theories and more standard, maybe like SU3 type gauge theories. Right there's no sort of non-trivial charge assignment we could choose that will keep every state completely stable, right? But for us, there are, right? And we've actually categorized all the different possible charge assignments which have this property. Yes, so unlike for this standard SU3 gauge symmetry, which we know from QCD, we can have non-trivial assignments which totally stabilize the dark matter with no need for some external stabilizing symmetry. But nevertheless, contact is still made with the standard model, because in each of these cases, we still have dark sector states which are charged under our U1, right? So we still have some states which talk to the dark photon, and in principle can communicate with the standard model. Okay, so we've talked about the decay of the pions. Next, it might be interesting to talk about how the rho could possibly decay. So if any rho meson is made a flavor singlet through charging under our U1 symmetry, then interactions of this form should allow the rho to mix with the dark photon, right? And so if it does this, it should have some decay mode where it decays back to the standard model. So we can think of it as two different regimes, right? If rho is heavier than 2 pions, then the rho is going to, this is backwards, excuse me. I should have corrected this. It should be that the rho is lighter than 2 pions. Then rho should decay democratically back to standard model FF bar pairs, right? The idea being if the threshold is closed for the rho to decay back to pairs of pions, then it has no choice but to decay to standard model states. But if the threshold is open, then of course the rho is going to decay dominantly back into the hidden sector, and this isn't going to be a signal that we can actually see. But there are still other ways that we can potentially look for this theory. Right? So yeah, one possible signature of this sort of theory is that, yeah, well, in general, these sorts of theories can lead to dark showers at colliders. So these are characterized by semi-visible jets. And what this means is that at colliders, if a Z prime is produced and it produces a pair of dark quarks, once they hadronize, we're going to have some number of states in our final state which are stable against decay back to a standard model. So they produce only dark jets, right? But if in the way that we've described before, we have maybe one state or more than one state which mixes with the Z prime and is able to decay back to standard model stuff, then we have QCD jets as well, right? So this is what we mean by semi-visible jets. That part of our jet will be visible and part invisible, right? And so this is sort of a unique signature of these types of theories and should help us look for them at colliders. An unfortunate fact, though, is that these searches are currently limited by event generators where it's not clear how we should be treating these sorts of non-standard gauge theories, right? Most event generators at the moment are quite specialized to more QCD-like theories, of course. But there are some other searches that we are thinking about. So first of all would be a standard bump search in the dilepton production cross-section, right? This is much more to do with the dark photon than our dark sector stuff, of course. But nevertheless, this is something that should be visible from our theory. And of course, there could perhaps be some more distinctive signatures from interactions of this type, right? So depending now on the stability of these outgoing states, we can get some pretty unique looking stuff. So if rho can decay to pairs of leptons, for example, then we have something like a dilepton plus missing energy signature to look for. But this is currently in the works. So something else which I probably should touch on is, well, what is...
Excuse me. In previous slide, I think you showed only nonlinear sigma model type Lagrangian for pions, and I don't think you showed the Lagrangian involving the vector meson explicitly. Yet, I mean, have you shown the explicit form of the Lagrangian involvement? My question is, where does this rho pi coupling come from?
I see.
Okay.
Yes, so this is something which I haven't included because it's quite a long expression, but this comes from the gauging of the Vess-Zumano action, right? So this comes explicitly from the anomalous sector of the theory, right? So if we have our Vess-Zumano action and we gauge it, we get exactly these sorts of interactions. So one way we could see this is that it's really just, it's very, very similar to this vertex here, right? The pi to VV. So what you could think of is that it's something like this AVV anomaly when we instead gauge the full flavor symmetry rather than just a U1 subgroup.
Oh, okay.
Yeah.
Thank you.
No problem. It's written explicitly in our paper. Maybe I can show it just at the end if you like. But yes, that's basically the idea. So when we gauge the full Vess-Zumano action, there's many terms involved, but we get exactly these sorts of interactions, pi to rho. Yeah, and of course, these exist in the standard model as well.
Sorry, one question concerning the signatures. Is the coupling of the V or the rho to standard model quarks much smaller than the coupling to the states in the strongly coupled sector?
Yes, it's suppressed by this. So if you like, it's suppressed by, let me go back, this parameter epsilon, right? So in principle, it's just a part of our parameter space, which we would hope to constrain. But yeah, the idea is that we allow some very small coupling, and that's going to be part of our parameter space. So
I see. So for phenomenology, the game is in a way to choose this parameter as large as possible in order to get a large production cross-section, but as small as possible in order to avoid bounds from digest searches, because this is, I mean, the couplings to the leptons are, I guess, model dependent, right? Because
that's true.
I didn't see directly where leptons come into the game here, but the couplings to the quarks are unavoidable because you use them for production. I see.
That's exactly right. But so it's true that they're model dependent, but actually this choice fixes them. So what you should be able to see, so if this is in fact your weak hybrid charge.
I see.
So what you can imagine is that, okay, if we now it depends, of course, how we tune the mass of this guy, this V. If it's sufficiently light, then really you have only coupling of the dark photon to the electromagnetic current. But there, every coupling is just going to be controlled by this parameter epsilon multiplied by the whatever the electric charge of the outgoing states is, right? So that's where the lepton coupling comes from. It's really just a product of this epsilon with the electric charge of whatever guy we're thinking about. But yeah, you're right. It is totally model dependent, and the dark photon isn't the only gauge field we could introduce. If we like, we could introduce a Z prime and arbitrarily charge everything on the standard model side. And then what we constrain is something like just the Bayer coupling itself, right?
I see.
But yeah, you're right. It is ultimately model dependent. This is just one example. So where was I? Yes. So one thing I wanted to touch on as well is well, what does the symmetry breaking we've talked about look like in the effective field theory? And well, the answer is mass splitting amongst the goldstones, right? So the relevant term in the effective field theory is this guy here, right? This is the term which gives us the same symmetry breaking pattern as that interaction term I wrote before. So what we do is now compute the corrections to this through one loop contributions to the goldstone self energy. So what we do is to take into account all contributions of order E dark squared. And so what this means is that we need to take into account also contributions which come from Z prime, well, V row mixing, right? That's the idea. So each of these sort of open dots includes not just the bare coupling of the dark photon to the pions, but also a contribution which comes from mixing with the rows, right? So after some computation, we get this leading order expression for the mass splitting now between charged and uncharged goldstone states, right? So this is, of course, a leading order in chi-pt. And all that means is that this contribution is independent of the pion mass. So what we could imagine is that even in the limit where we have massless pions, we're going to get some contribution to charged pion mass just from its coupling to the dark photon. And this gives us exactly that, right? Now, in principle, we're going to have contributions which are proportional to m pi squared and m pi to the 4. But at leading order, this is the dominant term. So one nice aspect here is that this is totally different symmetry breaking properties to any corrections with which come about from quark mass splitting, right? So we can still have fine splitting between our pions and totally preserve the EM stability, even while some of these states actually talk to the standard model. So I'll also briefly mention something which we discussed in our
in the previous slide, is MV is dark photon mass?
Yes, exactly. So dark photon mass and rho meson mass. Right. So these are the two guys which control the corrections to the pion mass.
Okay, thank you.
No problem. No problem at all. Yeah. So one thing which I wanted to touch on as well, which is also discussed in our paper, is this other source of symmetry breaking which we could have, which is, of course, mass splitting between our fermions. Once mass splitting is turned on, our global Sp4 symmetry breaks to an Su2 cross Su2. And the pseudo-number goldstone bosons always decompose into a 4-plit and a singlet of this remaining symmetry. So what this results in is mass splitting now between the flavor singlet and all of the off-diagonal states which form a 4-plit. And so what should be plain to see then is if we already have a flavor singlet, as soon as we switch on any standard model coupling at all, this guy is going to decay. So that's something which it's important to understand. This guy will decay. We lose this 3-to-2 cannibalization process because there's no longer enough goldstones to actually allow it to occur. And we need to think of some other way then of letting our dark matter freeze out. So yeah, one limiting factor then of the leading order chiral Lagrangian is that the GMOR relation, right, the expression which gives us the leading order masses of our goldstone, this actually predicts a degenerate spectrum. All right, it predicts that all of our guys are going to be degenerate even when we switch on mass splitting. So order MQ squared terms are going to allow us to break this degeneracy, which means if we really want a more valid description, we need to understand the next to leading order chiral Lagrangian. So I've included the potential terms which could contribute to mass splitting. So what we should be noticing here is that we have now these new LECs, A4 through A8. In fact, we have another number of them if we consider also the purely kinetic terms. And of course, these LECs are difficult to compute, right? We in principle need input from, for us, the lattice, right? There's no experimental data which we could use to fix these. It must come from the lattice, and it's costly to do. So it's something which we're interested in, but yes, it's probably still a while away. And yeah, of course, if these LECs are understood, then we can understand the next leading order corrections to masses and decay constants. In the full theory, however, masses and decay constants can be calculated from lattice. And we, for the first time, have results for exactly this case, right? So what we should be seeing on this is our flavored vector mass really is just a proxy for mass splitting, right, in lattice units. So the further right we go on this plot, the greater degree of mass splitting is present in our theory. And one thing that we can see in almost every, well, in every case is that at a certain point, when mass splitting is sufficiently large, there's this crossover between the lightest spin 1 state and the heaviest spin 0 state. So really this shows us that there is a point not very far from degeneracy where we conclusively lose this idea of Goldstone bosons, right? We can no longer say beyond this point that our pions are the Goldstone bosons of chiral symmetry breaking, because they're not even the lightest states. But I mean, just for a sanity check, that's, I guess, nice to see that we have this behavior. Okay, so just some.
Excuse me. In this plot, in the lattice result, so you have a so charged pion is heavier than neutral rho meson.
Yeah, so the idea, so I guess just to explain what this actually means, it's less about charges, it's more about diagonal states versus off-diagonal states, right? Because when we introduce non-degenerate fermions, all of our off-diagonal stuff will still have the same mass. But the idea is that if our mass splitting is sufficiently big, if it's big enough, then what we see is that there's a crossover, and then yeah, the off-diagonal pions actually become heavier than the flavor diagonal row.
Okay, so let me ask you some naive question. I mean, in the usual chiral Lagrangian for QCD case, where gauge group is a color gauge group is Sc3. In that case, we know that the raw mass is roughly speaking, raw mass is a cutoff scale for the chiral Lagrangian, which is non-normalizable, right?
Yes.
So rho is basically a cutoff scale because the chiral Lagrangian involving only pions cannot describe rho meson because it's out of the it does not appear in the Lagrangian from the beginning. So rho mass is a cutoff scale, but in your case, in this plot, for example, rho zero is lighter than charged pion, and that means that the if you so what is the cutoff scale here? I mean, rho. What would be the cutoff scale in your chiral Lagrangian without rho and with rho?
It's a good question. Oh, excuse me. Sorry.
Yeah, please. I'm done basically. Okay. If my question is not clear, then please let me know.
Sure. No, it's perfectly clear. So it's a good question. I understand completely. I guess the key differences to highlight between QCD and our theory is first of all, we're interested in working further away from the chiral limit, right? QCD is a theory which I guess is very, very close to the chiral limit, and that's what establishes this very large hierarchy between rho and pions, right? We're interested in trying to relax that assumption for a couple of reasons. First of all, would be that on the lattice, we're kind of stuck with working quite far from the chiral limit, right? It's very, very costly to work close to it. But I guess something that I should point out here is that since these results are calculated from lattice, which is a non-perturbative treatment of the theory, we don't have this arbitrary cutoff scale encoded in these results, right? So it's not for us a problem that at some point the rho zero becomes lighter than the pi plus minus, right? Because these are just lattice results. There we just look at and simulate the full theory, and we extract the LECs. But of course, this would be a problem if we were doing chi-pt in this region, right? That would be a huge problem. But that's not something we intend to do. I guess more this is to provide a very, very rough estimate of exactly where chi-pt is valid and where it's not. Okay, so I guess ultimately the answer is that that's not so much a problem because these are lattice results which intend to tell us exactly where this cutoff might be, right? Rather than something which is calculated from the point of view of chi-pt.
Okay, so another question, do you have a similar plot from the lattice calculation for the degenerate fermion case?
So I provide some earlier. Hope that this should still, yeah. So they do exist. I think I included a plot which should, where is it? So this would be the equivalent plot, right?
So here you have one pink band and
yeah. So the only relevant one would be for this upper band. The reason for that is they consider two different fermion representations in this paper, but this one I believe is the fundamental.
Okay, so if I look at the bottom right plot, then the horizontal axis is pseudo Goldstone boson, the pion mass.
Yeah.
And
right.
the vertical axis is a vector meson mass. Right. In this case, so vector meson is always heavier than the pion mass, right? More than two times, I think.
Yeah, but now of course the difference between this plot and our plot is that given that the fermions are degenerate, there is only one pion mass and one rho meson mass, right? There's no point at which these would ever diverge. They would be totally degenerate always. The point we were trying to make, I guess, with our plot is that once we switch on mass splitting, there's going to be a point at which the mass splitting becomes sufficiently large that no treatment in chi-pt could be valid anymore, right? Because as you say, there will be this crossover, and now we certainly could not identify pions as Goldstone bosons anymore because they're not even the lightest states, right? Like at some point along our curve, what we see is that the rho meson actually becomes lighter than some of the pions. Certainly we couldn't identify now pions in any way as Goldstones, and probably the description in terms of chi-pt is broken.
So another question, sorry for asking.
No, not at all. I think these are interesting.
For example, in the for this non-degenerate fermion case, you have some mass spectrum for charged and neutral pions and rho mesons. And my question is that when you write down the effective Lagrangian involving pions and rho meson for SP flavor symmetry case, can you fit this? Can you fit this lattice result by choosing some appropriate low energy parameter in the chiral Lagrangians?
Yeah, so this is again something which is addressed a little more concretely in the paper. The answer is yes to a point. The point, in fact, something which we wanted to address in the paper a little bit was just to understand, okay, is there any way of saving this leading order chiral Lagrangian in the presence of, you know, mass splitting. What we find is that if we're very, very close to degeneracy, then the answer is yes. If we're far from degeneracy, then no. And we really need to then look at higher order chiral terms and include all of these to fully capture the behavior. So yeah, the answer is yes, kind of. But what we establish from these sorts of plots is a pretty firm limit where no treatment in chiral perturbation theory would be valid any longer, right? At that point, it doesn't really make sense to perform this expansion any longer. But what we see is that we can even save leading order chiral perturbation theory if we limit our mass splitting to be quite small.
Yeah. And could you go back to the earlier slide where you show 3 pions and 5 row meson, etc.? Yeah, here.
Yeah.
So, you know, in ordinary QCD case, pion is my question is, I mean, this question is because I'm not very familiar with SP flavor symmetry was. So in the usual QCD case, pion is a QQ bar bound state where total spin is 0, spin singular state. So Q and Q bar each has a spin 1/2. So QQ bar can have a spin 0 or spin 1, right?
Yes.
So QQ bar spin 0 state make pions. QQ bar spin 1 state make row meson. And so they have a different the same number of flavor structure. And when we look at the Sp4 color gauge theory in the middle column, you have 5 pions, which I guess these pions are QQ bar bound state with the spin singlet.
Not only.
What is the row meson? In this case, QQ bar bound state in the spin triplet. Or I don't understand why you have 2 times more.
That's a real okay. That's actually a really good question.
Naive, I mean, easy answer to this question.
I do, yeah. That's actually a nice question. So thank you for asking. I'm glad I can mention this. Well, first of all, I should mention that what you say about pions being QQ bar bound states. Some of them are, but because of the peculiarities of Sp4 gauge theory, not only QQ bar bound states, right? We actually have also in our spectrum states which consist only of quarks or only of antiquarks, right? Because of pseudo-reality. Quark and antiquark have the symmetry between themselves, and what that means is that
I had also one more question about once you mentioned that in the pseudo-real theory, particle and antiparticle has a symmetry. What do you mean exactly by that statement?
I mean, one can actually exchange particle and antiparticle in the action
like
and leave it completely invariant.
Like a real particle, no?
Yes, like that.
Yeah,
exactly right.
So no, you cannot define quark number or conserved quark numbers or conserved baryon number, something like that.
No, well, you could. So if you like, you could introduce a quantum number which distinguishes them, and in fact, that's what we do in a way, right? When we charge them under our U1 symmetry, right? This is actually really what we're doing is we're introducing now something which lets us distinguish particle from antiparticle. But to begin with, they really are indistinguishable, and in isolation, it means that we have quark and antiquark states which are actually indistinguishable from the quark antiquark states, right? So they're truly degenerate with one another. And to answer your question about these different multiplicities, the way that you can understand this, I'm sorry, but I'll have to make an argument in terms of representation theory. The reason for that is that these two multiplets, they transform in different representations of the flavor group. So this kind of distinguishes this theory from standard model QCD, where both the pions and the row mesons transform in the adjoint representation. Here, pions transform actually in the antisymmetric 2-index representation, and rows, as usual, transform in the adjoint, right? So this is really how we can understand the sort of differing multiplicities of states, right? It's just because of pseudo-reality, we actually have these two multiplets are actually transforming in totally different representations of the flavor group.
Mathematically, I agree with you. Because I mean, number of pions are related with the number of broken generators, and the number of row meson is, in a sense, related with the number of unbroken generators.
Exactly.
So, I mean, in the SP and gauge theory, they can be different, right? As you mentioned.
Mm-hmm. Yeah.
So pion and row can have different numbers. Mathematically, I understand it. But in naive Koch picture for the meson following the ordinary QCD type argument, I'm a little bit confused. I mean, so pions are QQ bound state or QQ bound state with a spin singlet, and rho is QQ or QQ bound state with a spin triplet. So ordinary QCD case, pion and rho is a kind of they are basically same except for the total spin.
Yes, that's true.
In this case, it's not, because number of particles are different. So my question is, what would be the naive Koch model picture for pions and row meson in SP and gauge theory?
Honestly, it's a good question. I guess the way we've always understood this is in terms of representation and representations that they transform in, and also by I guess actually looking at the flavor structure of the bilinears, right? But actually performing a transformation and seeing that this produces only 5 and this 10 distinct states. But it's a good question, actually. It's a little more difficult to see, I guess, from the purely physics point of view, why this happens. And why, for example, we have, if we were to include axial vectors, then again, we have a 5 and not a 10. But yeah, it's a good question. I'm not sure I can answer it right at this moment.
So sorry to jump in here. Sean, do you happen to have the bilinears anywhere in the slides? What we are talking about is that you have different number of bilinear combinations that you can write down for pions versus rows, right?
That's true. I don't, but I can pull them up if you like. I can pull them up and show you, I guess. That's not a problem. 1 second. Should have that saved somewhere. It's at the end of our paper, I think.
Exactly.
Just a second. I think it's right at the end. Okay. Yeah. Okay, so I'll zoom in here. Can people see my? Yeah, so these are the bilinear sourcing each of the different types of states. So just to explain, this pi 1 through pi 5, and then pi a through pi e, if you like, these are the sort of generator basis. These are the standard QCD-like basis of pion states. And these are the row mesons, which we've been talking about, right? These are our axial vectors.
Okay, so this page is from your paper?
Yeah, exactly.
Okay, I'll take a look at them more carefully. Yeah. Okay, I see. So maybe I guess, yeah, in SP4 case, I think there would be baryons carry a integer spin, so basically baryons in your theory is also bosons, right? So maybe
that's how you could think about
you don't distinguish meson and baryons and include the usual baryons as I mean, just a row or pi, etc. Probably that's what you are doing, I think okay.
Yeah.
I think I can roughly figure out what's going on now. Yeah. Thank you.
No,
Thank you.
you're exactly right. You're exactly right. So
Okay.
these things which I called dikeworks, these Q, anti-Q states, these really, if you like, these are the baryons of this theory, right? They're the lightest sort of color neutral combination of just quarks or just anti-quarks that you can make. But because of the flavor structure of this theory, that they are indistinguishable from mesons, right? So they form part of the same multiplet.
Right. Thank you.
No problem.
Sorry to jump in from this slide. Is it true that all your pions are pseudo-scalars, but the rows are real, not pseudo-real? Because I see gamma 5s in the currents coupling to it with the pions, but no gamma 5s to the rows.
Well, so that could be a little bit. I guess the way I'd put it is that they may actually be present and absorbed into the definitions of these guys. As far as we're concerned, it really is a case where at least we can define a parity where all of the pions are pseudoscalars and all the rows have the desired quantum numbers. It's not a case that these things aren't present. It's just if we were to expand some of these guys, we should see. I should see that they have the proper flavor structure.
I see. Yeah. So they have varying parities actually.
Varying parities under the ordinary definition, but one can construct a parity where they have exactly the same parities, right? This is not a problem, I guess. It's sort of an arbitrary definition, but we can choose a parity under which they're all truly parts of the they truly have the same parities, every member of the same multiplet.
I see.
So this is the distinction we make between P parity, which is the ordinary definition, and D parity, which is something we construct just so that we can see that states of the same multiplet can be described as parity partners as well.
I see. Thank you.
No problem. So I can go back and do my conclusions, but one sec. Okay. Just be a second. I realize I'm running over, but I'll just go through exactly what we did, right? So, of course, we outlined the sort of background to dark matter, which is one of the most important unanswered questions in physics. Explained how strongly interacting theories can sort of naturally explain some of the properties we expect from particle dark matter theories. We constructed the low energy theory of PNGBs for SU4 to SP4 symmetry breaking. We used hidden local symmetry to couple the lightest spin 1 states to the PNGBs in the hidden sector. We've coupled a hidden, a simple U1 mediator to our hidden sector and described totally the associated symmetry breaking patterns, described the decays of the hidden sector particles and their associated phenomenological consequences. And yeah, moving forward, we're trying to model this and constrain it using fine rules and various event generators. Okay, so this is everything I had to say. We've had quite a lot of discussion, but does anyone have any further questions?
I have more questions, but I asked too many questions, so please ask.
No, not at all.
I think somebody else first ask questions. No question. So let me ask a couple of questions. Here you say this model is a minimal realization of the simple scenario. So in what sense this is minimal compared to QCD-like, I mean hidden QCD?
The reason, I guess I understand your point. The reason I guess we would call this minimal is that it has the smallest amount of matter content, right? It has the fewest number of fermions that we could reasonably include and still have this simp-like freeze out. So it's not a question, I guess, of complexity, but more of multiplicity, right? This is the fewest number of fermions we could introduce and still have this simp-like freeze out.
Okay, another question is that you showed the table for the bilinear representation of the mesons. And in that table, you also show the axial vector 1 plus state. And are there the lattice calculation, lattice results on the axial vector meson mass, decay constant, etc., or not?
The answer is not yet. At least we haven't put them out, but that is, of course, something members of our group are thinking about. Now, Suchida, you might have to remind me, but I believe we do know that they are certainly heavier than the other states, right? That's certain. It's just a question of how much heavier and if they're decoupled or not. I guess for most of what I discussed here in terms of chi-PT, we assume that they were decoupled. That may or may not be the case, depending, but it seems anyway that early results show that they're likely much heavier than the vectors, and so can probably safely be ignored.
Yeah, for example, you may know that in the ordinary QCD case, pi rho A1 system, there is a well-known Weinberg sum rules, which is a kind of a spectral sum rules for and the axial vector spectral density. And are there something similar in this SP flavor symmetry case or not?
I would expect that there is. I don't know for sure. That's not something we've checked, but I think it would be perfectly within our understanding of SP4 chi-PT to expect that there would be. Yes. Yeah,
it would be interesting to look at this because the number, in your case, pion and pion and the axial vector meson have the same number, and the rho meson is twice as many as the pion or A1. So it would be interesting to see how this spectral sum rule matches different number of particles in vector sector and axial vector sector.
Yeah, this would be interesting, actually. It's a good point. Probably something I should make note of.
Okay, thank you very much.
Yeah, great. Thank you. Thank you for the very interesting questions.
Thank you, Suchita, for joining this seminar.
Thank you for allowing me to join. I think listening to this discussion has been very educative for, I think, both Sean and me. So thank you very much.
Absolutely. Yeah. So does anyone have any further questions?
Just have a brief question concerning simulations. You mentioned you have a Fein rules implementation of this model. And are you doing any collider simulations for the dark showers already?
The answer for dark showers is pretty conclusively no. And that's for the reasons which I mentioned, where current event generators are not suited to simulating these sorts of theories. That's, I guess, sort of a limitation, which is that they're very specific to QCD right now. And for that reason, it's not so easy to do dark shower simulations with this sort of model. It'd be of course, would be something we would love to do, but it's just not there right now. We're looking at some other signals right now, which could hopefully help us place constraints on our model from elsewhere.
I see. So you're stimulating prompt signals like dileptons or dijets.
Yes.
And
exactly.
with dark showers, this is left for the future, because I seem to remember that I think the people working on dark QCD, like for example, the group in Oregon, Graham Cripps et al., have been making some attempts in that direction, but I don't know how they solve problems technically.
Sure. There, I guess, it is quite different, because for us, we have a theory which is really quite distinct from QCD in a lot of ways, which won't be apparent, I guess, to the current event generators. So for example, what we can see is that, as I understand it, the way that Pythia handles sharing is to treat all off-diagonal states as basically the same, right? And this, we know that this is already not valid for our theory, right?
Okay.
Different shared assignments could have very, very different phenomenology, and not every.
So,
yeah.
So you're saying the problem is basically with color and color flow in Pythia.
Yeah.
Yeah. Okay. I see. Thank you.
No problem.
Any other questions? I see no more questions. So let's thank speaker. Thank you very much for the nice talk.
Yes, thank you.
Thank you very much. Thank you.
Yes, thank you.